This lesson we're going to dedicate to talking about solids and different types of solids and how those properties are derived. I'm going to do a little bit of DJing. I'm going to show different videos here, but I'm going to try to put all the videos in one single video so you don't have to go to multiple locations. So classification of solids, there are four types of solids. There's metallic solids, there's ionic solids, molecular solids, and covalent network solids. I won't read how each of them is defined. You can just pause the video now and read it. But this video should go over each one of them. The one thing that you need to know is that when we talk about a specific solid, you need to keep in mind that a solid is an aggregation of molecules. And then you need to think about the aggregation of the molecules as a single substance, but you have to have in the back of your mind that each of those solids can be broken down into tiny substances, which we call a representing unit. So for example, the water here, it's a combination of several water molecules. This is the representing unit, and sometimes we show the formula. This is the chemical formula. The same thing can be said about table salt, right? So this is the structure of table salt. This is the representing unit. So is sodium chloride, NaCl, and here's the chemical formula. This is a quick reminder, or not reminder, refresher. By the way, I forgot to mention this to you. I'm going to put the link of this presentation into the video. If you want to follow, you can actually change and put your own notes. So you can use this as a way to take your own notes in addition to the notes there are in here. And I can actually open the notes here so you can see. So there's a place here for you to take notes. Okay. There's a place here for you to take notes, but also there are a lot of definitions here at the bottom, so you can utilize that. All right, so determining the types of compound, this is a refresher. If it is a metal bonded to a non-metal, you have ionic. If it is metal combined with metal, is metallic. If it is a non-metal combined with a non-metal, it is covalent. In covalent, we have two different types of covalent, and we're going to talk about them later on. But so that's how you break down whether it is metallic, ionic, or covalent. All right, so let's begin by talking about ionic. Here's a quick definition of it. I'm going to start by playing a video explaining ionic solids. A lot of this lesson, today's lesson, is a review, actually. So you're going to see a lot of familiar terms.
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 23. It's on ionic solids. Over the next 4 videos, we're going to talk about 4 types of solids, and what those solids are depend on where their atoms are coming from. So on the periodic table, if we were to draw a line like this, on the left side we're going to have the metals, and on the right side, including hydrogen, we're going to have the nonmetals. And so if that solid is made up of just atoms from the metals, we call it a metallic solid. If it's only nonmetals, but they're relatively small, we call those molecular solids. If they have large structures of covalently bonded atoms, we're going to call that a covalent network solid. And in this video, we're going to talk about ionic solids, which are a combination of metal and nonmetals. And so ionic solids, remember, are going to be made up of, or their structure is made up of ions, which are atoms that have either gained or lost electrons. They're either cations or anions. And so they're put together based on these almost static charges. And so how big those static charges are going to be based on Coulomb's law. And so if they have large charges, it's going to have a better structure, or lattice energy, we call that. And if they're smaller, it's going to have greater structure. And that's because they're closer together, those charges are. And so what are some of the properties that we observe in ionic solids? Well, they have a high melting point. They have low vapor pressure. They're going to be very brittle, break readily, and also they're going to be poor conductors of electricity. in a solid form. However, if we were to melt them, they can actually conduct electricity. And if we were to dissolve them in water and create a solution, they're going to conduct electricity as well. And actually making solutions of ionic solids is relatively easy if we use something that's polar like water. And so what does an ionic solid look like? It looks like this. And so it's going to be this nice lattice, and it's alternating ions. And so we're going to have anions like chlorine ion, and then cations like sodium ion. And what's happened is, remember, we transferred an electron from one to another, and then they're held together by almost a static charge. And this is an incredibly hard charge. And the reason why is that these are highly charged, these different ions, and also they're really close together. And based on Coulomb's law, opposites are going to attract. And as we decrease that radius between them, we're going to increase the charge between them. And so that's the structure. It's simply this nice lattice of ions. And so then you should understand the different properties. And so what's one big one? High melting point. Since these are attracted together with a really hard ionic bond, we're going to have high melting point. So this is salt right here. Its melting point is 801 degrees Celsius. If we look at sugar, which looks the same, but it's actually held together with covalent bonds, it's going to have a much lower melting point. They also have a really low vapor pressure. What is vapor pressure? Remember, if we put a liquid in a container, the amount of atoms that jump off and form a gas is going to be the vapor pressure as they exert vapor pressure. And so remember, the greater the forces are in that liquid or in that solid, the lower the vapor pressure is going to be. And that's based on, again, these high attractions in the ionic bonds. It's also going to be incredibly brittle. What does that mean? If we were to attach a ionic solid and just pull it from the sides, it'll break right in half. If we were to do that to a metal, it would stretch. It's ductile. Why is it brittle? Well, all of these ions don't like being next to other ions. You can see that all the chlorine ions are as far away from chlorine as they can get, and as we start to force them towards them, they push back. And so that's why they're going to be incredibly brittle. They can't conduct electricity because we don't have a lot of free electrons around. It's simply locked into this lattice. However, if we were to melt it, and so this is a lithium fluoride, beryllium fluoride melted salt, it actually starts to conduct electricity. And if we add it to water, it's going to quickly break apart, and it's going to be an electrolyte. It's going to allow electrons to flow through it as well. Why is it that we can break down ionic solids using something like water? Remember, water is polar. It's going to have partial negative charges on the oxygen side and partial positive charges on the hydrogen side. And so you can see that all the negative sides of the water are going to be attracted to the sodium. And so they can kind of usher it away from the ionic solid. Likewise, on the chlorine ion, what we're going to have are the positive hydrogen parts are going to be attached to it, and that's going to usher it away as well. Once we remove those water molecules, it goes right back to that ionic solid again. And so did you learn two things? Did you learn to show a representation of what an ionic solid looked like? And remember, it's just going to be ions that are locked together in a lattice. And did you learn the properties? The properties are simply built on the structure. And I hope that was helpful.
All right, so this is just another picture showing the representation of why ionic compounds are brittle. Just so you can digest a little bit more in terms of properties. So this is a representation of an ionic solid. You have positive and negative, so the cations and anions. When pressure is applied to it and they begin to shift, there will be a repulsion because the cations want to be far apart as possible from the other cations, or the anions want to be far apart as possible from the anions because they have similar charge. So that repulsion is going to cause them to crack, and we call this a brittleness. Okay, so that's the idea behind. So then let's jump into metallic solids. Again, I put a quick definition of it here for you to understand. Again, I'm going to DJ this video here. By the way, let me close the ionic solids because I don't need it anymore. And then metallic. Here we go.
Talk a little bit about metallic solids. And here is an example of what a metallic solid might look like. They tend to be shiny like this. Some would say lustrous. Some of you might be guessing maybe this is some type of aluminum or silver. It actually turns out that this is sodium. Our same friend sodium that we saw bonding with chlorine to form sodium chloride and form ionic solids, it can actually bond with itself with metallic bonds. This right over here, you might guess is silver or something. It actually turns out this is calcium. And I know what you're thinking, isn't calcium kind of this chalky white powder? Well, no, those are compounds formed with calcium, things like calcium oxide. But this right over here is pure calcium. And the reason why it has to be in this container, it is highly reactive with oxygen. So that's not oxygen that is in this container. It's some form of inert gas. But calcium, when it just bonds to itself with metallic bonds, which we'll talk about in a little bit, it also looks kind of similar. It's this shiny, metallic, or lustrous look to it. And what do you think this is? Well, this is something we're used to associating with metals. This is gold. But once again, you can see it has this lustrous property. So what is it about metals or metallic solids that allow them to be lustrous in this way and have other properties that we're about to see? And to understand that, we just have to look at the periodic table of elements. And most of the periodic table of elements is actually some form of metal. You have in red right over here, this group 1 elements, not including hydrogen. Those are your alkali metals. And you have your alkaline earth metals, your transition metals, your post-transition metals, your metalloids. And it's really only what you see in yellow and blue here that are not your metals. So how do metals form solids when you just have a pure sample of them? Well, the general idea, you can look at your alkali metals. They all have that one valence electron. And to get to that stable outer shell, it's much easier for them to give away a valence electron. And that's why we often see these folks participating in ionic bonds. They can be ionized quite easily. But if you have a pure sample of them, they can contribute electrons to a sea of electron, one each. These alkaline earth metals, they have 2 valence electrons. They too can be ionized, or if you have a pure sample, like in a calcium, they can contribute 2 valence electrons to a sea of electrons. And the transition metals here have a similar ability to contribute valence electrons. And so in general, we can view metallic solids as having cations, these positively charged cations, in a sea of electrons. So you have all these electrons here. I'll just try all these minus charges that they're in. Where does those electrons come from? Well, if you're looking at the alkali metals, each of those atoms could give 1 electron to that sea because it doesn't really want that valence electron. If you're talking about alkaline earth metals, they can each donate 2 electrons to that sea. Now, given that you have this positive charge in this sea of electrons, what do you think are the properties? How good do you think this will be at conducting electricity or heat? And many of you might guess, if you looked at a wire, wires are made out of metals because they are excellent at conducting electricity, or they tend to be excellent at conducting electricity because you have all of these electrons that can move around. And so if you apply a voltage, they will start moving and conduct electricity. And those electrons can also be good at conducting thermal energy or heat. Now, what would be, we already talked about them having this shiny, lustrous property, but how easy would it be to bend them? With ionic solids, we talked about they can be strong but brittle. As soon as you try to shift them around a little bit, they can break. But what do you think is going to happen here? If, let's say right over here, I were to push really hard, and on the top, I were to push really hard to the left. Do you think this will be brittle, or do you think it will be malleable? It's easy to bend. Well, if you have a pure metallic solid, it's actually quite malleable. If you just took this top part and pushed it to the left, like this, no big deal. You have those cations that are still in that sea of electrons. And that's generally true of metallic solids. They are very malleable. They are not brittle. In fact, so much so that oftentimes we want them to be a little bit more rigid. We want them to be a little bit harder. And that's why we might do things like add other elements into the metallic solid. For example, pure iron is reasonably malleable, but if you want to make it stronger, you could stick carbon atoms in between. For example, you could put a carbon atom there or a carbon atom over there. And that way, it kind of disrupts this electron sea a little bit, so it's not quite as malleable, and it'll be stronger and more rigid. So I'll leave you here. This is just an extension of what we've already learned about metals and metallic bonds to just realize why most of the periodic table of elements that we're familiar with has some of these properties when you have pure solids of them.
Okay, and one thing that he mentioned towards the end, and I wanted to bring up again. So a lot of times we want to design different metals for a specific purpose, and one thing that comes part of it is what we call an alloy, which is a metallic material that contains one or more elements, and that totally changes the properties of the element. So now we can kind of modify based on our needs. And I know this table is very hard to see, but hopefully you can see some of them. But this is things that you may or may not have encountered. For example, brass is an alloy, is a mixture of different metals. Bronze is another type of alloy, is a combination of tin and copper. You also have stainless steel. So there's a lot of different substances that it's a combination of different metals. Okay. Next is molecular solids. Those are pretty straightforward because it's really tough to get molecular solids. And the reason for that is because they're covalently bonded, but what's holding them together is intermolecular forces. And you know that intermolecular forces are pretty weak. So it's kind of hard to find them as a solid. You have to cool them down quite a bit in order to find them as a solid. So therefore, they have very low melting point. They have low conductivity to no conductivity. They're very volatile. It's easy for them to go into gas. Right? Here's an example of them. This is carbon dioxide. It has to be very, very cold in order to be a solid. And you can see they kind of just aggregate together. And the only thing that's holding them together is intermolecular forces. And here's an example of iodine. Again, you have to cool it in order to make it into a solid. Okay, so those molecular solids. A really important one is covalent solids. That's covalent network solids. And what's really special about them is that they form a network. Okay, so this is a nanotube, I believe, and this is a bulky ball, and we're going to talk about them in a second. But the really neat thing about this, and doesn't have to be for all of it, but it's actually just made out of carbon. And again, they're covalently bonded. So let me play the video about that one.
Molecular solids, which is formed from individual molecules being attracted to each other through intermolecular forces. Now, what's different about covalent network solids is that they're entire networks formed by covalent bonds. What we see here, for example, is a network of silicons and carbons, and this is silicon carbide right over here. And now some of you might be thinking, haven't we already seen covalent bonds involved in a solid before? For example, in molecular solids. And this right over here is an example of a molecular solid that we studied in that video. You have the molecules, which are made up of atoms bonded with covalent bonds. But the reason why they form a solid is because the molecules are attracted to each other through intermolecular forces. And if you wanted to melt this molecular solid, you have to essentially overcome these intermolecular forces. While in a covalent network solid, the solid to a large degree is made up of these covalent bonds. And if you wanted to melt this somehow, you would have to overcome these covalent bonds, which generally speaking are stronger than these intermolecular forces. And so you can imagine covalent network solids are going to have higher melting points. You also don't see a sea of electrons here, so unlike metallic solids, they're not going to be good conductors of electricity. But just to understand this point a little bit more clearly, let's look at some more covalent network solids. So what you see here on the left, you might recognize as a diamond. A diamond is just a bunch of carbons covalently bonded to each other, and this is the structure of how these carbons are bonded. And as you might already know, diamonds are the hardest solid that we know of. These covalent bonds, the way that they are structured, can take a lot of stress, a lot of pushing and pulling. It's very hard to break it. Now, what's interesting is that same carbon can form different types of covalent network solids. For example, this right over here is graphite. And graphite is probably something you're quite familiar with. When you write with a pencil, you're essentially scraping graphite onto that piece of paper. And so this is what graphite looks like. It's these covalent network sheets. And each of these sheets actually are attracted to each other through intermolecular forces. And that's why it's easy to scrape it, because these sheets can slide past each other. But if you really wanted to melt graphite, you would have to break these covalent bonds. And so you can imagine, to overcome the covalent bonds and melt, say, diamond or graphite, it takes a very, very high temperature. Graphite, for example, sublimes at 3,642 degrees Celsius. The silicon carbide that we looked at the beginning of this video, it decomposes at 2,830 degrees Celsius. This right over here is a picture of quartz, which is a very common form of silicon dioxide, another covalent network solid. And this has a melting point of 1,722 degrees Celsius. So the big takeaway over the last several videos is there's many different ways of forming a solid. It could be with ions, it could be with metals, it could be with molecules that are attracted to each other with intermolecular forces, or you could have a network of atoms formed with covalent bonds.
All right, so the one thing that was not mentioned in the video, and is pretty important, is that those network of those network solids, they can also form something else, what we call a polymer. A polymer molecules, they have a high molecular mass, so that they're pretty heavy, and they're bonded together in a repeating unit, what we call monomers. Some example of polymers is silk, leather, cellulose, DNA would be another example of a polymer. Again, they're just combined together into this massive network. Okay. I want to show you here is an example of how we use all those different types of solids into engineering. This is an example of a car. So you have under the hood here a lot of semiconductors, because there's a huge electrical component to the motor, obviously. Mainly they use silicon. Here, anything you think of plastic, you can think of polymers. So just again, it's a combination of monomers, usually covalently bonded. You have here your alloys. Remember, alloys are metallic bonding with additional atoms added to it. So here you have stainless steel, you have just plain steel. You have another polymer here, that's your tires, right? Those are elastomers. You have platinum here, so a metallic bonding. You have alumina, which is your ionic solids here. And then you have another type of alloy. So you can see how this the different types of bonding and the changing properties are super helpful in designing and engineering. So the videos talked a lot about properties, but we haven't talked about some common properties when we describe solids. So I just want to bring them up now. When we think of properties, you really have to think of electrons. How loose are those electrons? How the electrons are being shared? That's what comes down to. So in the videos from the Khan Academy, I talked a lot about ductility and malleability. I just wanted to bring it down what they are. So malleability is the ability of a substance to be hammered or pressed into shapes. So anytime you're able to hammer or press something to a shape, we call that a malleable. If something is not malleable, something is brittle, right? Ductility is the ability to be drawn into wires, okay? And again, all comes down to how are those electrons shifting. So for example, I have a substance here, in this case is a metal, and I apply pressure to it. The way it deforms, the way it moves, if it just is able to slide past each other but still connected, we call it malleable. It can even be ductile if it's able to string it into a wire. But for example, if we apply pressure and all of a sudden you find repulsion within the substance, it's likely to crack. So we call this brittle. Okay, so that's what comes down to. That's how we design things for ductility and malleability. In terms of conductivity and luster, we talked a lot about shininess. So shininess is We call it luster, and it comes down to, and it has a definition right here, is the ability of electrons to absorb light and re-emit light, right? So we study this when we study fireworks. So it says right here, okay, exactly what I said before, and that's what makes them look shiny. Conductivity, so far we haven't really differentiated between conductivity of heat versus conductivity of electricity. That's because they usually go hand in hand. But again, this ability of electrons to absorb and release, absorb and release. And here's an example of heat conductivity, and here's an example of electrical conductivity. Okay. So this is my last slide, and just a quick overview. So there are 4 types of solids. We have metallic, we have ionic, we have molecular, and we have network. Their properties, again, are based on where the electrons are at, so either through bonding or through intermolecular forces. So metallic, ionic, and network, they're all through bonding, where this molecular here is through intermolecular forces. That's how they are put together. And then there's some common properties of solids when we talk about malleability, ductility, luster, and conductivity. Right, so you guys should be ready to start your lab now.